Hello there. Last time we have seen how the EPR spectrum of any radical or other species can split into various hyperfine line due to the interaction of electromagnetic moment with the nuclear magnetic moment, and we call them the hyperfine splitting. We saw a lot of examples where the splitting comes from the spin half nuclei, particularly from proton. And we saw certain patterns that we can see in the spectrum when there are many equivalent spin half nuclei are there. And we said that one can use the Pascal triangle to find out the number of lines and their relative intensities. So, here we have this triangle again displayed here. So, when there is no nuclear spin, we get one line, let us say in the middle. Then we have one spin half nuclei, it is split into two. So, this much is the splitting due to the nuclear spin. So, if I have got two nuclear spin, then again it is split by the same amount here from this to this gap is same as this gap there, but the intensity ratio becomes 1:2:1. That way we can build up the various possibilities for any number of nuclear spins. Today we are going to generalize this idea of many equivalent spin where the nuclear spin is more than half. Last time we have seen several examples of this kind. One example is here, that this free radical tempole. Here the unpaired electron interacts with the nuclear spin of nitrogen, and we saw that it gives EPR spectrum of this kind where three lines are have equal intensity. Let us recapitulate how we arrived at that. First, that electron spin in a magnetic field splits into two because of the spin half, ms equal to minus half and plus half. Now, this interacts with the nuclear spin of I equal to 1 or mi equal to plus 1, 0 and minus 1. These are the possible mi values. Similarly, the upper energy level is also split into 3, plus 1, 0 and minus 1. And the transition involves the change of the electron spin from this to this without changing the nuclear spin. So, we got 3 transitions of this kind. Yes. So, since all these 3 levels are almost equally populated, we get the spectrum with intensity ratio of 1:1:1, which appears in this fashion, 1:1:1. So, this gap is same as this gap, which is a measure of the interaction of the nuclear spin with the electron spin. All right. We also saw copper complex, which is of course a very complicated one if we see it. Now, this spectrum comes from the naturally occurring copper complex. Now, naturally occurring copper has 2 types of isotopes, copper 63 and 65. So, to understand the origin of this, or rather to simplify this spectrum, let us look at the spectrum where we have only one enriched isotope, that is copper 63, and here is the spectrum. Of course, spectrum has become simpler than earlier, and what it shows is that there are 4 lines of different intensity. By intensity, if we mean the height of this one, that this height is bigger than this, which is bigger than this, and this is the least height, but same time if you notice carefully, the widths are different. So, one has to be careful in deciding what the intensity is. So, for an absorption spectrum, which looks like this type of thing. this is a magnetic field. We normally say intensity is area of this. Now that is related to, let us say if we take the full width and the half intensity of this and measure this one, the height of this one. So this I will call delta B half, that is full width at half maximum of the intensity, and this one, this let us call it I, then this area is proportional to I into that we all understand. But the EPS spectrum that appears here is in the form of a derivative line. So what can you say about its area? For a derivative line, the shape is of this kind. So if you simply add this area and this area, this is going to give area will be equal to 0. So that is of no use. We have to somehow therefore relate this intensity to this type of intensity. So what is done here is the first you convert the derivative signal to an absorptive signal of this kind by integration. That is, you start from this end and keep on adding this area, various slabs are taken, and then keep on adding this little small strips, and then continue to do this all the way to the extreme right. So then it will give an absorption profile of this kind, and then the area of this can be calculated in the similar fashion as this one, or one can actually do a numerical integration of this kind, add all these little strips, then I will get the area of this one. So further integration gives the area. Okay. Now one can go through this numerically with the advantage of computer. This can be done very easily, but one can also get a very good approximation to this in the similar way that we have done it here by measuring the full width or half maxima and this width intensity here. So here similarly, in a similar fashion, we can define two quantities. One is this intensity, let us call this peak to peak intensity. So that is from the top of this to bottom of this one, I call it I peak to peak. And in analogous manner, that the width that is used here, we can define a width from this to, maybe we will use a different color, this to this. So you could extend this one, this width, from this peak position to this peak position, and I call it delta B peak to peak. So in this case, the area of this, after doing all these two times integration, the area that we find here will be, this area will be proportional to this I peak to peak times the width that we have here, delta B peak to peak square of that. So it is not the product of this and this, the way it comes here. The reason is simple, that we have to integrate it two times to get the area. First integration gives this, second integration gives this one. That is why this comes in the form of product. So because this area is now proportional to the width square, even a small change in the width can really change the height of the signal quite appreciably. Now that is seen here, that width of this line is slightly broad, in fact broader than this one, this is broader than this one, this is broader than this one. So this is the narrowest line. So consequently the height is maximum here. So if we can integrate all these areas either by computer or in the absence of that we can even manually find out the height of all these lines and also measure the width of this peak to peak, and if we calculate it, we will find that all 4 of them have exactly same intensity. So, that means that the apparent intensity difference is not of any consequence, it is the intrinsically all 4 lines have the same intensity. So, why 4 lines are coming now? It is easy to understand. The nuclear spin of copper is 63. So, the way we have seen here, the 3/2 is the nuclear spin. So, this will split into 4 lines, this will also split into 4 lines, and then I will get 4 transitions of equal intensity, and that is precisely seen here. So, why these lines have different width is something we will not try to understand now, but we will understand later. For the time being, we notice that this is indeed a very special feature of this copper complex. When you compare all the spectrum that you have seen for free radicals, where the line widths are essentially same for all hyperfine lines. Now, to understand this spectrum now, we try to see, let us look at this, the various nuclear properties of these 2 isotopes. Where is the difference? Copper 63 has about 69% natural abundance, 65 has 30% or 31% to be more accurate. Both of them have got the same nuclear spin, 3/2 and 3/2 here. So, what I have got in this spectrum is actually 2 types of complex. One has got copper 63, other has got copper 65. So, both will therefore split into 4 lines. Because the spin of this, let us say this is for copper 63. Now, copper 65 similarly will give similarly 4 line spectrum, and because its nuclear spin is also 3/2. What we have is a superposition of these 2, but when you superpose them, will they exactly overlap? Let us try to understand that first. Now, center of the spectrum, which is here for this is here, will they be same for these 2 species? What decides the center of the spectrum? That comes from this relationship, that so this value, G factor or G value of this one. So, both the spectrum are recorded in this at the same time, because sample had 63 as well as 65. So, they experience the same frequency. So, the difference can come if they have got different G factor. Now, can G factor be different for these 2 species? The G factor is an electronic property of the molecule. So, it depends on how the electronic structure that the molecule has. Now, when I have got these 2 isotopes, what is the difference? Difference is only in the nuclear isotope. Now, and copper nuclei is reasonably heavy nuclei. So, for such heavy nuclei, usually the electronic wave function does not depend on the nuclear mass. Only if the nuclear mass is very light, for example, hydrogen atom, when you have got either it is proton or deuteron, the wave function can slightly be affected. But otherwise, this difference is so, the mass is so high compared to the mass of electron that this will have no effect on the electronic structure of this complex. So, the G factor will be same for both of them. So, in other words, the center of the spectrum will be same for both the species. Then, where else can the difference be? Is the splitting going to be different? We do see that splitting is different here, that if you see very carefully, this side there is a small hump is there. So, it is possible that it could come from overlap of 2 hyperfine line. Similarly, this is obviously coming from 2 hyperfine line which are overlapping here, though it is not very clearly seen, only part of this line is seen here. So, it indicates that this splitting that we see here and here they are not quite the same, but only evidence is that we see some sort of difference here, but they are overlapping here. So, can the hyperfine splitting constant be different? Further, we go back to the table of the properties of copper nuclei. You see that magnetic moment of copper 63 is 2.43 and for copper 65 is 2.54. Indeed, the magnetic moments are different. Copper 65 has slightly bigger magnetic moment than copper 63. That means the electron in the copper complex sees a little bigger magnetic field that is created by the 65 nuclei. So this splitting will be just a little bit bigger than this one. This will be slightly bigger than this one. Now, how is it going to change? So, this gap will be just a little bit bigger than this gap. Similarly, from here this gap will be still bigger than the gap that is here. Same way, the gap that is here will be little bit less than the gap that is here, and the gap between this to this will be much smaller than the gap that is here. So, now you can imagine that if we now overlap these two, I will see a spectrum which may look like some sort of splitting here and maybe a little bit splitting here, but more prominently here. And the top of that, the width of these are not same across this from right to left. The widths are more here and least here. So, what happens in the process? The resolution is such that is going to be such that this will be seen much more clearly than this one. And when you take the derivative, we get let us say here we get one line which looks like this one, this type of derivative signal, and other line this type of thing. So, there is a partial cancellation of this part of the spectrum with this part of the spectrum. So, net result is that we get a spectrum which looks like this type. Here the lines are broad, so what we see is small hump compared to and not so well resolved line here. What is more, you see that copper 65 here has about 31% natural abundance and 63 has 70% or 69%. So, this intensity is correspondingly going to be, contribution of this will be somewhat smaller, well by the exactly the same ratio. 30% intensity will come from here and 70% will come from there. So, we will see this will have a smaller signal than this one, and that is exactly what we see here. So, we understand how this signal appears. Again, the width changes gradually from the rightmost to the leftmost signal. Okay. The other example we saw earlier is this di-vanadilyl complex. This complex has two vanadilyl center here given here, VO and VO there, and they are connected by this oxygen bridge. There are other part of the ligand is not shown here. It is these two bonds here, these two, and there are a lot of things around this one, which are of not much interest to us. So, all that shows that these two vanadilyl, the way they are bound and form the complex, they look completely equivalent. So, what sort of spectrum we expect from this two equivalent vanadilyl complex? This is the spectrum that appears here. So, we see that again the widths are not same. Unlike the copper complex, where the width increased gradually from right to left, here the narrow lines are in the middle and broad lines are at the two sides. Lines are broader here and also here. So, that again we will not try to understand the origin of this right now, we will postpone it to some other lecture, but right now we will see if the intensities are same or not. Here we go through a similar argument that width and height together decide the intensity, and for derivative line we use this formula. We will see that intensities of these lines are not same. The intensity changes gradually from here, becomes maximum here and goes down in this way. Okay. So, how does one account for these different intensities now? So, now having learned so many different types of nuclei now, it should not be difficult for us to generalize say, this to this particular case for vanadilyl complex. For that we find out the magnetic properties of the vanadium nucleus. See, vanadilyl complex has the nucleus vanadium, it has two isotopes V50V and 51V. So, here the natural abundance is only 0.25% for 50V and 99.75% is 51. So, we can as well assume that this is absent there, and the spectrum that we see here is coming from this isotope, and its nuclear spin is 7/2. So, 7/2 means how many lines I will get? Now, from all the discussion that I have seen here, it will give 8 lines of equal intensity for only one vanadium. Then the second vanadium is going to split all the lines further, and I have shown it here. So, if this is the line position in the absence of any vanadium, then when you have got one such nucleus of vanadium whose nuclear spin is 7/2, see this splits into 8 lines now. This is the center, so this splits such a way that this gap is equal to this gap and this equal to this gap. So, the 8 lines are split are seen here. Now, that is due to the first nucleus. When I have the second nucleus, each of these lines are going to split further by the same amount and same number of lines. So, 8 line comes from here. See, the gap between this and this is same as gap between any of this line here. Okay. Similarly, this line is split into again 8 lines, and that way all the other lines are shown here. So, what I see here therefore is that at a given position more than one contribution comes. So, here therefore, count the number of lines that I can see here. This intensity 1, there are 2 lines come there. So, the intensity will be 2, that if you count all of them, there will be 15 lines with the intensity given here 1, 2, 3, 4, 5, 6, 7, 8, 7, 6, 5, 4, 3, 2, 1, and this is what is seen here. Though it is not very obvious, one can actually integrate these various lines and come to this conclusion there. So, this shows that vanadilyl complex, when there are 2 vanadilyl there, is perfectly understandable from the whatever we have learnt here, the way the various Hyperfine line that appear there, and how equivalent nuclei can produce different type of line intensities. Okay. So, can we generalize this Pascal triangle that we have seen for spin half system? We are trying to do that now. So, here the Pascal triangle is shown for spin 1 nucleus. Let us see how it is created. It starts from the line intensity 1 where there is no nuclear Hyperfine interaction, and now there is suppose number of such nucleus 1 which I is equal to 1. So, then this will split into 3 lines with intensity 1:1:1. This can be found out by adding 3 numbers, comes from these 3 that is appear at the top of that. One is directly above, other is from the left, other from the right. So, here we can assume that there is 0 is here, 0 there. So, this 0, 0, 1 gives 1. And here I get these 3 lines from here, here, and 0 is here, then this gives 1 there. Similarly, this one I get 3 numbers from here, here, and imagine 0 there, then I get 1, 0, 0 gives 1. That is fine, 1:1:1. That is what we have seen in case of tempole. Now I equal to 1, but n equal to 2. So, we follow the same argument now, that to get a number here, I try to find out the number which is directly on the left in this above and right. So, I have got here 0, 1, 1 gives me 2, but here then directly above is 0, 0, 1. So, this gives me 1. Then if we, what is the intensity here I can expect? I get in value 1, 1, 1 gives 3. Similarly here 1, 1, 0 gives 1, 1, 0, 0 gives, sorry, this gives 2, this gives 1. So 1, 2, 3, 2, 1 is the relative intensities of spin 1 nucleus, and whether 2 of them are present there. That way we can generalize this, that every time I get number from here, for example here I get add the numbers which is directly to the left and above and right. So 2, 1, 0 gives 3, that way the numbers are created there. So this is not Pascal triangle, but very much like the Pascal triangle. We add 3 numbers, one is the left, right, and in the right directly above. Now we have seen the copper spectrum where spin is 3 by 2. Can we create a Pascal like triangle for 3 by 2? Again, procedure is very similar but not quite the same, and the triangle is shown here. When there is no Hyperfine splitting, let us say the intensity 1 is here. Now when one spin 3 by 2 splits the line, there will be 4 transitions. So to get this 1 is to 1 is to 1 is to 1, all I do is that I add now 2 numbers from the left and 2 numbers from the right. Now let us see how it is done there now. I will get 4 transition here, 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 here. So imagine 0, 0, 0, 0. So to get the intensity here, I add 2 numbers from the left and 2 numbers from the right. So this and this together gives a value 1 here. Now for similarly here, I add these 2 numbers from left and these 2 numbers from the right, this gives me 1. Then to get the line here, I add 2 numbers from this left and these 2 numbers from the right, gives me 1. And similarly here I add this and this gives 1. So this looks simple, 1, 1, 1, 1, but let us say, do we understand the procedure correctly? So for that we go down once more. If we have 2 such nucleus of spin 3 by 2, then each of the lines will split into 4. So there will be line here and line here, and for this and over here, here. Similarly for here, here. So to get the intensity here, I have this is 0, 0, 0. I add these and these to get a value 1. Then to get the intensity here, I add this and this. So then I get a value which is 2. To get the value here, I add this 2 and this 2. So this gives me 3. So then further this will give me this and this gives 4. Then this and this gives me 3, 2. So 1, 2, 3, 4, 3, 2, 1. That's the way the line numbers are created here. So you can check if really you can figure out how these numbers are found out. So we see that Pascal triangle is a triangle which works for spin half system, but we can generalize this thing for other type of nuclei as well. We have generalized it to I equal to 1 and I equal to 3 by 2. Now we are going to generalize this pattern that you have seen here and summarize what we have seen for various nuclei. So if there are, let us say, n nuclear spin, and with a individual spin angular momentum is, let us say, little I, then the total angular momentum becomes n times I. Here for example, when you have got I equal to 1 here, Now, with this little I, we change the notation to small I for in each nucleus. Now, when the two of them are there, n equal to 2, then my I becomes 2. Similarly, when I equal to 3 by 2, when n equal to 2, two of them are there, then total I becomes 3. Okay. So, then total nuclear spin quantum number becomes n times I, and its component will be minus I to plus I, changing in units of 1. So, total components equal to therefore 2I plus 1. So, each of these produces a local magnetic field that the electron sees. So, there will be number of hyperfine lines given by this number 2 times I plus 1. So, those many lines will be seen there. Now, if this total I happens to be an integer, then there will be line at the center. Why? Because then 2I plus 1 is an odd number. So, odd number will give a line at the exactly at the center, and if I is a half integer, then 2I plus 1 becomes an integer. So, there will not be line in the center here, for example. Here 3 by 2 was there, so there is no line at the center here. And the relative intensities will be given by the Pascal triangle for spin half nuclei, and analogously for other nuclei we can generate a triangle of similar kind. Okay. The summary is that all EPR spectra are characterized by the basically three things. One is the line position. The line position for any of the spectrum here is given by this relationship, that is essentially given by the G value, and the width. It is also very important property. We saw that for most of the organic free radicals the widths are very similar, but not necessarily true for transition complexes like copper complex or vanadial complexes, widths are different. And of course, the hyperfine splitting and how many of them are there and their relative intensities. These are the characteristics of EPR spectra. Now, having learned this much, it is time to decide that whether EPR or ESR mean the same thing or not. I mentioned in the first lecture that we must discuss this and come to an agreement after some time. It is time we did that. You see that spectrum comes from the magnetic moment of the electron. Now, magnetic moment can come either from the orbital motion of the electron or the spinning motion of the electron, or it can come from both. You see the relationship between the angular momentum and the magnetic moment. If the magnetic moment comes from the spin angular momentum, then this is the relation, mu is the magnetic moment, G beta S, S is the spin angular momentum. And if it comes from the orbital motion of the electron, then orbital angular momentum L and magnetic moment due to L are related in a very similar manner. Only difference is the value of G that is used for spin angular momentum is about 2.00 something. These numbers are not of very consequence to us, and the G value that is used for orbital motion is precisely equal to 1. So, that is where the difference is. Only difference in the quantity of and not quality. Qualitatively both are very similar. Most organic free radicals have very little orbital angular momentum. So, in that case calling them ESR spectrum should be okay, but the system, for example, in which has both motion due to S and L, that is magnetic moment coming from the orbital motion and the spin motion, what will you call them? Think about it. Now, it is also possible that system has no spin angular momentum, but it has an orbital angular momentum, and the magnetic moment comes from that motion, and we can get a corresponding paramagnetic resonance spectrum. Then calling it an ESR spectrum would be simply wrong, because there is no spin motion present in the particular system. So, here is an example. Oxygen molecule we are all familiar with, and its electronic configuration in the ground state is shown here. 1s, 2s, 2p are the orbitals of the oxygen atom, and there are 8 electrons there, and these middle lines, these middle horizontal lines are the molecular orbitals. So, these 8 electrons from one oxygen atom and 8 electrons from the other oxygen atom produces this set of electron configuration, and you must have read in your MSc or maybe undergraduate. Here important thing is that these 2 electrons are unpaired here, they are occupying 2 different pi orbitals. So, that produces this triplet state of the oxygen molecule. So, oxygen molecule in the ground state is a paramagnetic species, and one can actually see its EPR spectrum. Now, if this oxygen molecule is excited, it produces a singlet state, and it produces 2 types of singlet states, and the way the difference is, you see here these 2 spins are parallel, but one of the excited state is that these 2 become anti-parallel now. But since these 2 occupy different orbitals, this can be a singlet state, and that singlet state is has this sort of electronic configuration. Okay, this excited state, but it can have another excited state where these 2 electrons are forced to stay in a one molecular orbital. Then naturally the spins are necessarily going to be paired. So, this is a singlet state, but this pi orbital gives rise to a net orbital angular momentum of lambda, which is equal to 2, gives rise to this delta state. So, this electronic state is 1 delta G has no spin angular momentum, but orbital angular momentum, and one can see its magnetic resonance spectrum, which is shown here. So, this singlet oxygen gives rise to these 4 lines, and this spectrum also other line which is present here, which is very intense, it actually comes from the ground state of oxygen, triplet oxygen there. So, you see that one can see the EPR spectrum of a molecule which has no spin angular momentum, but only pure orbital angular momentum. So, this cannot be called an ESR spectrum. By the way, I must point out that this looks like hyperfine line that we have seen so far, but in oxygen molecule, which is this nucleus has 16, this also 16. So, this has no magnetic moment, this also has no magnetic moment. So, these lines that are appearing here, though they look like hyperfine line, but they are not. This is interesting that something else is seen here. This experiment was done in the gaseous phase. So, we take oxygen gas in the spectrometer and try to look at its paramagnetic resonance spectrum. So, here the oxygen molecule undergoes rotational motion, and rotational motion are also angular momentum. So, they can also give rise to a coupling of angular momentum to the orbital motion of that, and that can produce such lines which appears as if they are coming from certain hyperfine interaction, but that is not so. Anyhow, coming back to this, that certainly this cannot be called an ESR spectrum. So, electron paramagnetic resonance is a very general term now, which includes both paramagnetism coming from orbital motion as well as spin motion. So, we will continue to use the term electron paramagnetic resonance in these lectures. So, with this we come to an end of this discussion.